Well, as it turns out, some logarithms became more popular than others. Not like in a social sense, but just out of, sure repetition. And that's why they called them, some of these, common logarithms, because they happen so commonly. Now don't worry about that b is greater than 0 stuff, or b is not equal 0. Don't worry about that, okay? What we need to understand is if we look at this, once again, logarithms, they go either way. So I should be able to take a logarithm and change it into an exponential form, but also the exponential form into logarithm form. But the most common that happened was this base 10 business, which we've seen, because our place value system is base 10, right? So we have our ones position to the left of a decimal. And then if you multiply that by 10, then you have the tens position. Then if you multiply that by 10, you see the base 10 business right there, okay? But also if you divide by 10, then you get some decimal tenths, hundredths, thousandths, and so forth, right? Now we're not going to go too deep into that, of course, but that's why it happens so commonly, because if we change place values, we're looking at base 10 stuff, all right? So the difference between these two, and it should go both ways, all right? If I see a base 10 in a log, I can write it as a common log right here. Well, what's the difference between these two? This one shows the base 10. This one does not. It's not a 0 by itself. So if I saw something like this, log of x, I would expect you guys to know what the base is on this one. Now it's not shown. If you feel better by showing it, then write it in. It's a base 10 because it's so common. All right, so this kind of creates a chain for us, right? If I had a base 10, I'll use a different color. Base 10 to the power of y, and then we'll say this equals x. Well, we could easily change this into a log with the base 10. No, that should be an arrow right there. There we go. Log base 10 of x. Now again, you don't really need the parentheses right there. And that log would equal the exponent of y. Now this may be important because, well, eventually we'll start solving for the exponent. However, we don't really need to, and again, if we wanted to change that into exponential form, we need to be able to. But if I wanted to change this and just said, you know what, I don't like writing that stinking base, then I've got log common, so it's just log of x. Then it would equal the y value. It means the same thing, you guys. So if I saw log of x equals y, I could change it immediately into base 10 of, exponent. Let me start that over. Base 10 to the power of y equals x. It's the same thing. Bam. Find the common logarithm. Okay. Well, this is a log, and the log usually equals a y value. Now, y is not the answer, but we just have a variable there to solve for. Now again, it's a common log because it didn't show the base, so if you wanted to, you could see it's base 10. So if I change this into exponential form, I should have used purple right there, right? Then I would have 10 to the power of y equals the 10 right there, okay? Well, if that's the case, then 10 to what power equals 10? And again, if you wanted to see the exponent of that 10, you could write a 1 in because it didn't show it. Well, that just means that 1 equals the y, which means the original common log of 10 equals 1. That's our answer right there. That may have been more explanation than you needed, but that's how the math works on that stuff. All right, let's try this one. So that's a log, and it's going to equal y. And then the base, if you like it there, you can see the base 10, right? Well, that means our base for the exponent is 10 to the power of y. This is going to equal whatever that was the log of, which is 1 over 10 billion right there. Okay. Well, then what is the y value on this thing? Okay. We got 10 billion right there, which is just kind of like a 10 to the power of, how many zeros is that? 10 of them. Now that's 1 over 10 billion, so it's going to be a negative exponent on that. So that equals 10 to the power of y, right? Which means that y has to equal the same exponent right there, and we'll actually see that as a rule later on. So y equals negative 10, and well, that's our answer right there. I kind of did that, I think, what we would consider the easy way. Let me go deeper into that. So 1 over 10 billion would be 0.123456789 1, which equals 10 to some power. Well, if I make y some positive power, then I just get bigger and bigger values. But this is an extraordinarily small number. So to make it a small number, it's kind of like I'm moving the decimal to the left. So I've got to make it a negative exponent. Okay. There is an easier way. Here is the easier way. Well, let me. This method is, roughly, we would call it the calculator method, where I'm going to find the log button, which for me is the second button down from the top right, left. It's right under my second button. So I am going to push that button, which is called log. And when I do that, it gives me a parentheses already, which was extremely generous. And then I'm going to type in the number 0, and then don't forget your decimal on that, right? How many zeros do I got right there? 1, 2, 3, 4, 1. And then after I type that number in, I'm going to push enter or equals. Then it will give me the answer. My calculator gave me -5. That is all. Like this one, evaluate your calculator giving at least 3 decimal places. Here's the problem with this one, is if I changed it into an exponent, I would get 10 to some power equals 83. Okay, well, you can start estimating in your head, right? 10 to the power of 2 is 100, so it's got to be less than that. 10 to the power of 1 is 10, though, so maybe like 1.58, 1.8, maybe, you know, if you're lucky. However, it did tell us to use a calculator on this one, which is highly recommended. So I'm going to push log, the log button, then 83 equals, I meant 1.85. Let's, my calculator gave me 1.91907. I don't really need any other decimal places because it said 3 decimal places. So I look at the 9. To the right, it's a 0, so it stays a 9. That is all. 1.919 is my final answer. All right, once again, using a calculator, again, I'm going to push the log button. Then I will type this value exactly like I see it, 0.0042 equals, and now it gives me a negative 2.37675. And again, the rest doesn't matter, because I only want the third decimal place. However, if I look to the right, the 7 is bigger than 5. Let me rephrase that. It's 5 or bigger. So that 6 is going to add 1 right there, which makes it a 7. So it would be negative 2.377 is my final answer. This brings up an interesting point, though. I guess it's slightly different than that last one. Why is this answer negative? Does anyone know? So the log is of some value that's smaller than 1 as a decimal. So it has to be a negative value. Bam. All right, just before we put this one in the calculator, would we expect this answer to be positive or negative?
Positive.
Positive. It's never going to ask you that on the homework. But just in case we got like a negative value, we could see that we would have typed it in wrong. My calculator gives me 3.11. I'll just round it for you guys right there. Is that okay? Do you guys want to see the whole number? I'll show it. Fine.